Hello everyone, I am Mr. Kabir Inamdar. With my co-authors, I present quantum selective helium isotope separation via graphene nanopores, a theoretically framework. So here is the outline is as follows. We start with the separation challenge and why membranes, especially graphenes, are the solution. Then we cover the quantum physics deep Broglie wavelength, zero point energies that is ZP and the WKB tunneling model. We introduce our unified QTA matrix, validate it with the TMM method that is transfer matrix method and show the flux selectivity and the outcomes. Finally, we discuss the strategies to boost plus multi-stage enrichment, future work and the conclude. So here is the separation scenario in the chemical industry. Separation processes like distillation, drying and separation etc. consume 45 to 50% of all the energy in the chemical industry. That's nearly half. This high energy cost is exactly why we need better alternatives like membranes. We sit at the low energy end. This sets the stage for why we turn to the graphene membranes. So we discuss why membrane technology. Look at the table. Membranes are very thin for the fast gas flow. They have tiny exact pores for the high selectivity. They are strong and work well in the tough conditions. They use less energy and are easy to the scale up. Now, why do we need membrane-based separation, special graphene? The question is arise in our mind. So answer is that the membrane saves 90% of energy, produce no waste. Porous graphene is easy to build and operate, perfect for the separation. Now, these slides cover the periodic table position and the property of the helium. Helium is a noble gas with the two isotopes, that is He3 and He4. Out of this, He3 is very rare. Mass difference changes their quantum behavior and the tunneling. That is our starting point. Now, this slide explains why we separate helium-3. Helium-3 is very rare on Earth, used in security and the fusion purpose. Supply is very low. Traditional methods are costly and cannot separate it. So we need a new way to separate helium-3. This slide is the heart of our work. Chemically, helium-3 and helium-4 are identical, but quantum properties differ. So quantum, not chemistry, enables separation. Now, let's talk about our barrier height. We have chosen 0.5 electron volts. But is this realistic? Yes, let me show you why. Perfect graphene is 11.7 electron volt, tetravacant 1 electron volt, hexavacant 0.4 electron volt. So our value matches linears and Sayers. Then we add quantum tunneling through the QTA, WKB and TM model. That is our novelty. Now let's see research positioning flow. The field is the helium separation with the graphene. Existing study used DFT and WKB, but lack of unified framework, ZP model and validation. We fill this gap with the QTA, TMM and the rapid screening. So our work brings together many fields, quantum membrane, two-dimensional materials and graphene nanopores. We study quantum transport and tunneling. Our goal is helium isotope separation as well as isotope selectivity. This is useful for the nuclear energy and the cryogenic application. So here is the timeline of the literature positioning. It began in 1969 with the polymer membranes for helium. In 2004, Jim and Oslo isolated graphene. Then from 2008 to 2009, porous graphene was made. The real shift came in 2010 to 2012 with the quantum tunneling model using WKB and DFT. Later functionalized pores and resonant bilayer membranes appear. Most work is theoretical and focus on hydrogen. In 2026, Dogma ETL show that copper with the oxidation state first sides bind with the helium for the absorption, opening a new field. So roughly 50 years of progress. We identified 8 main gaps in the literature. This include application gaps, quantum and methodological gaps, design and performance gaps, experimental as well as the theoretical gaps. But the main missing piece is the unified quantum framework for the helium isotope separation. So we identified 8 literature gaps. First, the application gap. Most study focus on the hydrogen, not the helium isotope. Second, quantum methodological gap. No clear distinction between pore diameter and the barrier width. No ZP model. No barrier shape comparison. Third, the methodological gap. No unified framework. No QTA metric and no flux pore density relation. Fourth is the computational gap. DFT and the MD are slow and expensive. Fifth one is the design gap, permeance, selectivity trade-off, and the complex functionalized pores. Sixth one is the performance gap, different units and the condition hinder fair comparison. Seventh is the experimental gap, no validation roadmap. And last one is the eighth gap, that is theoretical gap. Thermal averaging versus the fixed energy tunneling is unclear. So our work is addresses all it. Now let me quickly go through our key assumptions. We use the rectangular barrier with the height 0.5 electron volt based on science work and validated by DFT. We work in the cryogenic range of 5 to 50 Kelvin where tunneling dominates. We assume low pressure so helium atom acts as independently. We neglect adsorption and zero point energy because they are very small compared to their barrier. We use WKB for the tunneling which we validated with the TMM. And finally, we assume the ideal gas behavior as well as the single layer graphene membrane. We discuss in slide Gaussian versus rectangular barrier. We choose rectangular barrier because graphene is automatically sharp, only 0.34 nanometer thick. Rectangular gives QTA 19 for the helium-3 and 22 for the helium-4. Selectivity is approximately 19 and measurable plus. Gaussian gives QTA is approximately 68 and 79 respectively. Selectivity is approximately 31,000. But the flux is 0, it is useless. Our rectangular model is TMM validated. Gaussian is not. So we choose rectangular and realistic selectivity with the measurable flux. Now let's look at the quantum nature of helium. These slides cover the de Broglie wavelength. We explain its physical meaning. Then we show the calculated wavelength for the both isotopes from the 5 to 50 Kelvin. We also show the graph comparing them. Finally, we discuss the difference between quantum confinement and quantum tunneling. Now, why do we need quantum mechanics for the helium? The answer is the de Broglie wavelength. This wavelength tells us whether helium atom behave like particle or like a matter waves. De Broglie wavelength depends on mass and the thermal energy. Larger wavelength is equal to the quantum effects. So, at low temperature, our helium system behaves quantum mechanically. So the table shows the de Broglie wavelength for the helium-3 and helium-4 isotopes from the 5 to 50 Kelvin. As temperature increases, wavelength decreases. The ratio of helium-3 and helium-4 isotope is remains constant at 1.152. At 10 Kelvin, helium-3 is equal to 0.460 nanometer, helium-4 is equal to 0.400 nanometer. Compared to the pore diameter that is 0.400 nanometer and barrier width is equal to 0.036 nanometer. Wavelengths are close to the pore size but much larger than the barrier width. So the quantum tunneling dominates. Now let's look at this graph. On x-axis we have temperature from the 5 to 50 Kelvin. On the y-axis we have the de Broglie wavelength. The blue line is for the helium-3 and the red line for the helium-4. The wavelength decreases with the temperature. Pore size is equal to 0.4 nanometer, barrier is equal to 0.036 nanometer. Wavelength near to the pore, larger than barrier. So quantum transport dominate from the 5 to 50 Kelvin. Now, let's understand the difference between quantum confinement and the tunneling. Pore diameter control the confinement as well as barrier width control the tunneling. Both are important. So the different masses give the different wavelength and the tunneling probability. That is the heart of our separation. Now let's see the deep physics behind our model. This diagram shows the helium atom approaching the graphene barrier as a matter wave. Pore size gives confinement, barrier width control the tunneling. Heisenberg gives the zero point energy and the matter waves. Barrier control the tunneling. We use the WKB and the TMM model for the validation. Now let's talk about zero point energy, that is ZP. Why consider it? Because it is the real quantum effect. Even at absolute zero, confined particle has some energy. This energy depends on mass. So the helium-3 and helium-4 isotopes have different zero point energies. We will now show you how we created this our model. So the question is, why consider with zero point energy? So the zero point energy is the most fundamental property. Zero point energy comes from the Heisenberg uncertainty principle. Even at 0 Kelvin, a confined particle has some energy. It depends on mass. So helium-3 and helium-4 isotope differ. Literature confirms that ZP is real. We must consider it. Now, here is the key gap we identified. Study do not define the confinement length for the ZP calculation. The transport path is not the same as pore size. No standard method exists for the graphene nanopores. We consider two limits, barrier width and the pore diameter. Now, here is how we handle zero point energy. we consider two confinement limits, barrier width that is 0.036 nanometer and pore diameter 0.4 nanometer. ZP difference is about 13 millielectron volt, that is about 2.6% of barrier for barrier width, and 0.1 millielectron volt, that is 0.02% for the pore diameter. Both are small, WKB remains valid. So the ZP is only a small correction. Now let me explain our specific approach to the quantum tunneling. We have rectangular barrier. We start with the exact transmission equation containing sinh. In deep tunneling limits, sinh simplifies. We drop the p factor because it cancels when we take the isotope ratio. Then we define the QTA as our unified matrix. TM validation follow in the next slide. Now let me explain why our WKB approximation is safe for selectivity. The exact transmission is the multiplication of the prefactor and the exponential. Prefactor affects the absolute flux, but we care about the selectivity, not absolute flux. For isotope ratio, prefactors cancel because barrier is identical for the helium 3 and helium 4 isotope. Selectivity comes purely from the exponential term, so the WKB works perfectly. Now let me introduce our key contribution, the Unified Quantum Tunneling Approximation, that is QTA. We define QTA as a 2 times kappa times barrier width. Kappa depends on mass, barrier height and energy. So transmission is e to the power minus QTA. So helium 3 QTA is 19.3, for helium 4 it is 22.3. The difference is about 2.94, giving selectivity is about 19. QTA is a single number that predicts the transmission and selectivity. It is analytical, validated by TMM, and clearly separate barrier width from the pore diameter. This is the heart of our framework. Now, the key outcomes of our QTA framework. QTA simplifies WKB to one number. It predicts transmission, selectivity, and resistance. It also separates barrier width from pore diameter. This allows for design comparison. Validated by TMM, QTA is greater for the rapid scaling. Now, let's see how barrier width affects the tunneling. This slide shows the QTA values for the helium-3 as we change the barrier width. Narrower barrier gives QTA is approximately 10, easy for tunneling but low selectivity. Our barrier is about 0.036 to 0.040 nanometer, gives QTA 60 to 19 balance the good flux and selectivity. Wider barrier gives QTA is about more than 26. It gives high selectivity but no flux. We choose about 0.036 nanometer for the best balance. Now let me show you how we validated our WKB model. We use an independent numerical method called as transfer matrix method. Why did we do for this? Because WKB is an approximation. We wanted to check if it is accurate. So we divide the barrier into the 1000 thin slices and solve the Schrodinger equation numerically. The result, the TMM and our analytical WKB match exactly up to machine precision. The error is practically zero. This proves four things. First, our math is correct. Second, our code has no error. Third, our barrier model is physically consistent. And fourth, all our results are reliable, so we can confidently move forward. Now let me explain why we validate our model. WKB is an approximation, it is not exact. So we need to know if our results are reliable. We use TMM as an independent method. It solves the Schrodinger exactly by dividing the barrier into the 1000 slices. This validates our WKB result. We will show the perfect match in the next slide. Now let's look at the validation result. Here is the comparison between our exact analytical formula and the transfer matrix method. Test case is about 0.5 electron volt barrier, 0.036 nanometer, 5 to 50 Kelvin temperature. Both the method match exactly for the both isotopes. Deviation is about 3.13 into 10 raised to minus 13, that is machine precision. So the WKB is mathematically correct. TMM independently confirm it. So what does this validation prove? It proves four important things. TMM validates our framework on four counts: correct math, error-free code, realistic barrier, and live calculation, all validated machine precision. So our selectivity, flux, and the performance results are completely reliable. Now let's talk about flux, the actual amount of helium that passes through our membrane. We break this down into the four parts. First, we have incident molecular flux. This comes from the Hertz-Knudsen theory. Let's us how many helium atoms hit the membrane surface. First, the incident flux, arrival of atoms. Second, quantum flux, tunneling through the barrier. Third, the total flux, combined. Finally, permeance, the experimental parameter. We will go through each of these step by step. Now, let's start with the first step, incident molecular flux. This comes from the Hertz-Knudsen theory. It tells how many helium atoms actually hit the membrane surface. Flux depend on pressure, temperature and mass. Higher pressure and temperature mean more arrivals. Heavier isotopes arrive slower, but this is just arrival, no tunneling yet. That comes next. Now, let's move to the next step. Quantum flux through the nanopore. Only a small fraction of atoms that hit the membrane actually tunnel through. The rest are reflected back. So the transmission flux is equal to the multiplication of the incident flux, porosity and the transmission probability. Porosity is pore fraction. Transmission from the WKB. Only high probability atoms pass. Without tunneling there is no flux. Now let's combine everything to get the total membrane flux. We use the WKB transmission probability, which is e to the power minus QTA. So the total flux for each isotope is incident flux times porosity times e to the power minus QTA. So the QTA is equal to 2 times kappa times barrier width. Higher QTA means the lower transmission and lower flux. Lower QTA means the higher flux. So the QTA directly controls the membrane flux. By tuning barrier design, we control how much helium passes. So the permeance is total flux divided by pressure difference. Higher flux gives the higher permeance. It measures the membrane's intrinsic transportability. Permeance is what we measure in the experiments. It directly connects our quantum model to the real world performance. So let me summarize our key outcome. First, WKB and TMM match with the nearly zero error. Second, QTA one number predict transmission and the selectivity. Third, high selectivity, transmission is approximately 19 and the flux approximately 21.7. Fourth, clear distinction between the barrier width and pore diameter. Fifth, quantum transport dominate 5 to 50 Kelvin temperature with the stable flux and selectivity. So the graphene nanopores are promising for the isotope separation. Now, how can we increase the flux? Here are 5 practical strategies. First, pre-enriched feed gives the more helium-3 flux. Second, higher pressure increase the flux linearly without changing selectivity. Third, more pores create the parallel path for the higher flux. Fourth, larger membrane area improves the throughput. Fifth, cryogenic temperature preserves the tunneling and the selectivity. Combining these boosts flux without losing selectivity. Now, let's see how we can achieve very high purity helium-3 using the multiple stages. Part first, table and formulas, that is the theoretical purity. Our single membrane gives selective 19. With the multiple stages, selectivity multiplies. That is 19, 19 square and 19 cube. From 10% helium-3 feed, one stage gives 68% purity, two stages gives 97.6% purity and three stages gives 99.8% purity. So in part second, process flow, that is the diagram. The flow diagram show raw helium gas first go through the pre-enrichment. Then it passes through the three membrane stages. At each stage, helium-3 permeates while helium-4 is the left behind. Finally, we get the high purity helium-3. Now let me quickly discuss our future work. First, develop bilayer graphing model and optimize interlayer distance for the selectivity. Second, extend to the multilayer membranes. Third, include realistic parameters and experimental validation. Fourth, investigate scalable system. These steps move us toward real-world application. To conclude, quantum tunneling enables intrinsic separation for the helium-3 and the helium-4. A rectangular graphene barrier gives realistic and measurable transport. Our WKB model is fully validated by the TEMM method. Graphene nanopores achieve high selectivity with the measurable flux. With three membrane stages, we predict over 99.9% theoretically helium-3 purity. Overall, our framework provides a strong theoretical foundation for the future helium isotope separation technologies. So, these are the key references that form the foundation of our work. So, the quantum tunneling in graphene nanopores offers a promising pathway toward efficient and scalable helium isotope separation. So, we conclude our presentation here. Thank you.